When a clinical probe rests against the skin, it transfers energy directly into the human body. Every image produced is the result of a physical, mechanical, acoustic wave interacting with living tissue. Unlike a CT scan or an X-ray, ultrasound relies entirely on the absence of ionizing radiation. Instead, the machine functions as a highly calibrated transceiver. It must emit high-frequency physical vibrations and simultaneously record the returning echoes. Operating this tool requires precision. A clinician must understand exactly how electrical energy is converted into directed acoustic energy. That conversion relies on specific hardware architecture, mathematical formulas that translate raw echoes into multidimensional formats, and strict biological safety margins. Navigating that pathway allows a diagnostician to maximize image fidelity without crossing the threshold into physical tissue damage. Peeling back the casing of the external transducer reveals 4 distinct internal layers, each built to strictly governed geometric dimensions. The core component is the piezoelectric material. In a standard probe, this layer is composed of an array of 256 individual crystals. These crystals are responsible for both sides of the acoustic exchange, generating the initial ultrasound wave and receiving the returning mechanical echoes. This diagram isolates the piezoelectric layer to show its structural requirement. To resonate correctly, the crystal must be manufactured to a thickness of exactly 1/2 of the operational acoustic wavelength. But the high density of this crystal creates an acoustic impedance mismatch when placed against softer human tissue. Without intervention, the majority of the sound energy would reflect off the skin and be lost. To solve this, a matching layer is permanently bonded to the front of the crystal array, acting as a step-down bridge for the impedance difference. To function, this matching layer must be machined to a thickness of exactly 1/4 of the acoustic wavelength. Looking at the rear of the array, a dense block called the backing material sits directly behind the crystals. When an electrical pulse fires, the crystal vibrates. The backing material absorbs backward-moving energy, preventing it from reverberating and returning into the crystal. This physical dampening directly determines the array's Q value, abruptly stopping the vibration to control the exact length of the emitted ultrasound pulse. Finally, an acoustic insulator wraps the internal assembly, preventing these intense microvibrations from transferring into the operator's hand. The transducer is a tightly constrained acoustic engine. Its sub-millimeter geometric calibration dictates the efficiency of the entire imaging system. Here, we see the fundamental unit of ultrasound data gathering, the A-line. A single acoustic beam fires sequentially into a tissue interface, hits a boundary, and reflects a distinct wave echoing back up to the source. The purest representation of this raw data is A mode, or amplitude mode. It plots the returning echoes as spikes on a simple one-dimensional graph. Historically, clinicians used A mode to detect midline shifts in the brain. Today, its application is almost entirely isolated to ophthalmology for measuring retinal structures. This animation illustrates B mode, or brightness mode, the foundational format for modern diagnostic imaging. Instead of a single line, 100 or more A lines are fired in rapid lateral sequence. The system receives the returning echoes and converts their varying amplitudes into a gradient of grayscale dots. Firing these lines sequentially builds a 2-dimensional cross-sectional image of the underlying tissue, slice by slice. By adding the element of time to these rapid B-mode pulses, the machine generates M mode, or motion mode. M mode tracks the depth of a specific tissue boundary continuously, rendering an image analogous to an unbroken video recording of movement. This temporal mapping allows cardiologists to calculate the exact real-time velocity of fast-moving organ boundaries, like a beating heart valve. The final primary format is Doppler imaging, which shifts the computational focus away from amplitude entirely, prioritizing flow and velocity. This diagram demonstrates the Doppler effect in action. When the acoustic wave strikes a moving object, like flowing blood, the frequency of the returning sound wave inherently changes. If the blood moves toward the transducer, the returning sound waves compress into higher frequencies. If the blood flows away, the waves stretch, decreasing the frequency. Depending on the velocity ranges required by the clinician, Doppler can be deployed in either targeted, pulsed waves or as a continuous operational beam. A, B, M, and Doppler are not separate cameras. They are distinct mathematical translations of the exact same mechanical echo, mapping acoustic data across amplitude, space, time, and frequency. Down at the cellular level, the physical reality of ultrasound becomes clear. Even without ionizing radiation, mechanical pressure waves force energy into tissue, causing biological strain. This diagram outlines the first major risk metric, the thermal index, or TI. This measures the ability of the acoustic beam to induce localized heating in human tissue. The index is a strict ratio. It divides the emitted acoustic power by the exact power required to raise the local tissue temperature by 1 degree Celsius. For routine clinical scanning, a thermal index below 0.5 is considered entirely below the threshold for any biological effect. However, that safe threshold drops severely if the patient is febrile. If a patient's starting temperature is already elevated, the tissue requires far less acoustic power to reach dangerous heat levels. The restrictions are absolute for highly sensitive tissues. When scanning the eye, embryos under 8 weeks old, or fetal neuroanatomy, the thermal index must never exceed 3.0 under any circumstance. Here we see the calculation for the second risk metric, the mechanical index, or MI. This tracks the maximum amplitude of the pressure pulse, which dictates the risk of cavitation. Cavitation occurs when rapid pressure changes from the ultrasound beam force microscopic gas bubbles in biological liquid to expand and violently collapse. The mechanical index calculates this risk by dividing the peak negative pressure of the wave by the square root of the ultrasound frequency. The British Medical Ultrasound Society mandates that the MI must remain below 0.7 for general diagnostic and obstetric imaging and strictly below 0.5 for neonatal scans. The risk of cavitation spikes dangerously when the beam passes through gas-containing structures like the bowel or lung, when utilizing low-frequency pulses, or when injecting ultrasound contrast agents into the bloodstream. Diagnostic safety guidelines limit how much acoustic power a machine can legally deploy into a patient. Zooming out from the cellular physics to the clinical workstation, these physical limits shape the daily reality of the radiologist. This B-mode scan provides an active readout of the physics. Top right, the machine displays the real-time safety metrics, a thermal index of 0.2 and a mechanical index of 0.9. These numbers represent an ongoing mathematical negotiation between machine, operator, and tissue. The operator must push enough electrical power through the piezoelectric crystals to generate echoes clear enough to construct a diagnostic image. But that demand for power is constantly bottlenecked by the necessity to keep the thermal and mechanical indices below the thresholds of physical damage. Operating an ultrasound machine requires a commanding grasp of acoustic physics. A clinician must constantly balance the geometry of sound to reveal the required medical data, while actively preserving the safety of the tissue they are investigating.